much energy and way too much excitement. I'm not going to do a good job. Those folks,
No, we're excited about what you're teaching
those
us.
folks are tired and beat down by now, so.
I am, I slept the 2 nights I've been here, I haven't arrived 4 hours.
Man,
Is that
hey,
your bike development?
hey, this is a big improvement from
Well,
like
thank you.
2017. Man,
I think I'll take that as a compliment.
Yeah, it is. I was gonna take it. I was cross-referencing it.
Hey, it's a lot better.
That's kind of the way I was thinking it. Thanks, bro.
Well, because like the 2014, you had like stick figures and no, I'm just kidding. he was drawing smiley faces.
All right. We've got to do a couple of major sections here this afternoon, but just this, did everybody get this? Okay. This is just somebody's notes. Again, this is a master's test, right? So, but it even is relevant to the journeyman specifically because of the sections, the type of questions and things. So I think this is a good thing to kind of talk about just real fast. But I have not gone through here to vet the answers that he's got listed here, but I did.
You got any extras of those? Sorry. You got any extra of those? I didn't get one.
Maybe
They handed them out. It came in late.
You came in late, sorry.
Came
You
in
were
late.
voting.
Oh, yeah, you can
Right on the-
Oh, I came in late too.
package. Huh?
I came in late too. Was there
Yeah, it
They
was
give
3
out a-
things.
today?
Yeah.
Oh.
Yeah, I think this was yours. wasn't it?
Oh yeah, yeah, yeah. Those right here. Yeah, he's still lying.
Do you remember 52?
No, I can take
Well,
it.
no, didn't your, well, what was the one that she
Oh,
said
she
that,
said that they had a guy videoed it, yeah.
What?
somebody videoed one of
Fucking portable glasses.
Hey, they got those ones for streaming. That board,
In Canada,
and you can stream at the
they
same time.
prepare,
Thanks, sir.
we have an interprovincial red seal exam, so everybody
Anybody
has
else?
a licensed journeyman in Canada. And so at the last day of school in 4th year, they would write the exam, and then they would keep the student allowance just for the guys that wrote the exam, the guys and girls. And they'd sit down there and everybody get together and say, what questions do you remember, right? And then the instructors would write these questions down, not so that they could give, but so that they knew if they were teaching material that was relevant so that people could pass the exam. You'd be surprised how many questions you'll remember after you write that exam.
That's very true.
You like, if you went out to your vehicle.
Oh,
with
yeah.
a piece of paper, and you'd probably
You
get
won't-
about 75%.
You won't forget. That's how Pat.
But the minute you pick up the phone or drive out of that lot, you're.
Lost half of them.
Yeah.
Just, you know,
Yeah, if you look at page 11, at the top of page 11, see if that kind of follow what you just said.
Do not leave the exam center until you write
Yeah.
notes down. Keep a notebook in your truck, and then as soon as you get out of the exam, before you drive off, write down whatever notes you remember.
What he just said is absolutely the best, probably the advice that I could imagine, because I can help you if I know what you're struggling with, right? If you drive out of that parking lot without writing it down first, you will go home and not remember, right? It's gonna happen. I mean, just first time you hit a stop sign, your mind's gonna go thinking about something else, and you'll lose some of whatever you just had. You're right there, it's fresh. So before you drive off, even if it's just a keyword, and you look for it, and couldn't find it, I can probably help you if you can remember the keyword, jot it down, right? You don't have to write down the whole damn question or anything like that. Just, you know, like if you had some particular calculation you were struggling with, or you had some kind of a question you didn't understand where to go with, those are the kind of things that I can help you with if you can write down at least enough of it that I can kind of get a feel for what they're trying to probably ask, right? So, you guys have a name tag, she gave y'all name tags, right?
Yeah.
My cell phone number is on the back of that. You can text me questions, you can take a picture of it and text me, you can email it to me, whatever you wanna do. If I'm not in the country, then text messages are probably better, because, I mean, eventually I'll get to it. Email is not quite so for sure, because that tends to pile up so much that I might miss it, but text messages are good. And then if you guys really are struggling with a particular calculation or section and you really want to get better at it, I'll do tutoring with you for free, hour at a time. I don't charge anything for it. You just have to schedule it with Melanie Chris, and she'll give you a time and date slot. And if you schedule with her, I promise you, we'll be there right?
Don't
Killing
spend
me. I got great intentions, killing me, yeah, let's do it, Thursday. Yeah, but she will make sure that Thursday comes, I'm sitting right where I need to be, right? So that's kind of the thing to do. And don't be shy. I mean, if you just want general help, whatever, it doesn't matter, right? It doesn't cost you anything, it's an hour.
The ones you got online, the YouTube ones you do have for the tutoring for the masters is really good, man.
Oh, yeah, and that's what that is, the tutoring sessions, right?
Yeah, the ones with, you get like 4 guys on
Yeah.
there, and then you're talking about, service,
That's not the porn one, right?
Oh.
Sorry. All right, let's talk about this real fast. And amperage of 48 and 60 amp for what? Oh, amperage of 40 volt, 50, 60, 50, 40 ohms, amperage. So Ohm's law, right? I don't really want to tell you too much about Ohm's law because I don't really want you to know much more than you absolutely have to have. So here it is. You see the in your code book is where it's at. Is where I want to point you to the right direction. There are 2 formulas that are the only 2 that you need to know, and they happen to take care of every single code section or code section on page 28. Those of you guys, these guys that are older school, you know, pi and ear and all that stuff, forget it. Can anybody tell me what that E stands for? I thought voltage started with a V.
P over I times R?
Yeah,
What is
they
it?
explained it, but I don't remember what they said. They said it was,
What's the actual word that E?
Energy?
Nope.
Oh.
Electromotive force, right?
Yeah.
I've never called a volt an electromotive force, ever. So for me, writing an E down is kind of confusing because I don't really recognize an E. I have to convert it in my mind mentally, right? A V, I know exactly what a V is, don't I? Right? What about I? What does I stand for? I thought that starts with a C.
Impedance.
Nope, that's resistance. What does the I stand for? It's amps, right? I agree, but I thought amps starts with an A. But what does the I stand for? Current. That starts with a C. So, I mean, you know, what does the I stand for? Intensity of current.
Intensity.
So, like, again, I don't look at a meter and go, I wonder how many intensity of current values I've got here. I'm looking at amps, right? So the EIR, the PIE, all that business that you learned with, forget about it. It just takes too much time to mentally reconvert that. So here's what we're gonna do. I know a V exactly as a V, right? I know an A is an A, and I know an R in this case is a resistor, right? I know a W is a watt, I know an A is an amp, and I know a V is a volt, and that is so much easier to instinctively look at. You know what those values mean, they match up. So volt, wave and bar. These 2 formulas are the only 2 that you really need to worry about, but you do need to know these 2 somewhat, right? If it has a resistor in the question, you know the only one you have up there to pick from is going to be the bar, right? If you're looking for a watt, and that's, you know, they give you a watt in the question, you're looking for value, then the only one you have up there is the W, right? You use this one all the time, so you're using this one not really instinctively realizing it, because that's what you do with an appliance. We're trying to figure out how many amps it is based on the system voltage, right? We're doing the math here. This line, as I mentioned yesterday or this morning, that's a division. So if I'm looking for a value down here, I've taken the other one and divided it into the top, right? If I'm looking for the value on the top, this line here stands for multiplication. So I'm multiplying those 2 values together to get the top value, okay? That's basically the formula that will circle. Sometimes you may see it, anytime Henry uses a triangle or whatever, it's the same idea, right? Same concept. It's division, multiplication. This value and this value are the product of the 2 at the bottom. And then the only other thing you need to remember is that these values need to be total values. In other words, sum of total at the branch circuit, the total of all those numbers, total volts, total resistance, total amps, for example. Or when I'm looking at a branch circuit, I could be talking about not the branch circuit value, but I could be talking about just the values that exist right here across one resistor, right? Or resistor number 2, or resistor number 3. And so I can do the same formula isolated here with just the values that exist right here at this one point. When I do that, I'm going to think about that like that as V3, R3, A3, so I remember these are individual point values and not total values, okay? Make sense? Now, I don't want to get the 3. Huh?
The 3?
resistor.
This,
Oh,
this being
okay.
position number 3, position number 2.
Yeah, I got you.
So you just, just counting them. Again, just because I wanted to make sure you remember that we don't wanna mix total values and individual point values, right? They're either all be just what exists there or all tons, sold ton. Sum total, okay? Make sense? All right. The other thing too, if you look on the top of page 28, I have parallel, these two little lines, the formulas written on the top of page 28. Where you see the AT equals A1. You guys already know that instinctively. In parallel circuits, if I have 15 lights in this room and each light is 1 amp, then I'm gonna take 15 times 1 and I'm gonna basically add or multiply it out and have 15 total amps, right? That's how it works. So the formula makes sense. It's AT equals A1 plus A2 plus A3 plus A4, right? The N standing for any number of additional values, right? But voltage in a parallel circuit, which is one of the reasons why we like to run things in parallel, is a constant value that doesn't change. So in a parallel circuit, 520 volts here. Well, what do I have here? And here, and here. Well, this is a series circuit drawn. I can't really say that. I mean, we're going to draw this here. Don't want to confuse you all any worse than I already am. All right. In a parallel circuit where I've got parallel runs, the voltage here, 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 they're all the same. Never change. I can count on that. In parallel. Now, if you look at the way we write that down is V1, or VT equals V1 equals V2 equals, so anywhere the same value across the board. In series, they just reverse position. Right? And I like writing it down like that because you can immediately instinctively realize what's happening here is what exists in parallel is the exact opposite in series circuits. So amps no longer add up. This is really weird. So you're telling me that if I have 10 lights that are an amp each and I add them together in series, it's going to equal 1 amp. Yeah, exactly. Weird. Right? It's weird. Amps do not add up. They're a constant value like your voltages in parallel. It's super weird, but once you get your head around it, I guess it kind of makes sense. But if I've got series PV panels, for example, if each one of those PV panels has 24 amps of output, and I put 10 of them in a string in series, I'm going to have a total of 24 amps worth of output. I do not get any additional add for amps in series. Now the good thing about that is that makes amps your ace in the hole, because if you know the value anywhere in that circuit, right, for a series circuit, anywhere in there, if I have one value for an amp anywhere in here, well then that's a key number, because then it's the same value anywhere else in that same circuit. Make sense? So just like voltage is our key over here in parallel, amps is our key in series. I want to find out what the amps are as fast as I can, because that's going to unlock everything in that circuit. All right, that's that part. Second thing to remember is that the volts drop 100%, or it's lost 100% across all resistive loads in a series circuit. So they write it as V1 or VT equals V1 minus V2 minus V3, but really the way we look at it is V1 plus V2 plus V3 equals VT is kind of the way we look at it. But every resistor in a series circuit is going to eat a certain amount of the voltage, and so when I come back out of that resistor and go into the next one, I've got a lower value for the volts than I had coming into it originally, right? So if this is 120 volts, for example, and I come through this resistor, I'm going to lose a chunk of it. Let's say that was, let's say it was a 6 ohm resistor, and this was a 3, and this was a 3 ohm. What would happen is I would lose 60 volts across that resistor. Okay? How do I know it's 60? Well, because it's a proportionate loss, right? If I have 6 ohms, 3 ohms, and 3 ohms, if those two bottom ones are also the same, well, that means I'm going to lose half of it on the top one and half on the bottom, right? And not only that, I'll be able to tell you it's 15 volts on each one of the bottom ones because it's a proportionate loss, right? What I'm getting at is if I have 120 volts coming into this and I lose 60, I'm coming over here down into this one with 60 volts. That's all I got left in the tank, right? When I go through that and lose 15 more, I come in here and I lose 15 more, I'm at 0 volts when I go back home. So I'm literally running out of gas, okay? In a parallel circuit, voltage is not supposed to drop or lose. It's always supposed to be the same value, but we do sometimes have a voltage drop, right? And that's that 3%, 2%, 5% business you guys know a little bit about. So don't get confused with a voltage drop in series versus a voltage drop in parallel. In series, it's 100% loss. It's a drop of all of it, right? So that's what I'm looking at, is how to distribute that total branch circuit voltage across those individual resistors in a proportionate manner.
You said 15 volts? 30?
I'm sorry, 30 is what I meant. Thank you. I didn't write it down. I said 30.
What's supposed to be 15 and 15? Right?
At least 60.
Oh,
30,
30,
30,
yeah,
yeah,
60,
one.
30.
Yeah, that's what I mean. I said 30, 30. Prove it. There's a kid like Anyway, thanks. Anyway, yeah, no, you're right, 30, sorry. But you get the idea, right? It's a proportion loss. The bigger the bigger that resistor is, the more it eats, right?
So if there was 4 of them, then it would all be less? Like, so you would start, would
Yeah.
it still be, would it start off with
Yeah.
like?
It's nice when your resistors are all values of a common number like 5, 10, 15, or 20, because you can almost do that in your head, right? If they're 3.5 or 6 and 12 and 8, I mean, it gets a little bit more messy because you can't really look at it cleanly. But at any rate, all right. Now, here it is. The two most complicated calculations you might possibly do would be resistors in parallel, which suck. I don't know how else to say that. Or if you're doing calculations for voltage drop, I think those are the two things that confuse people the most. And so I'm just going to quickly do a couple of quick examples and do this. Basically, I've got some slides here. I think it'll be helpful for you to see. I'm going to go kind of fast because it's something that, like I said, I don't really need to get too heavy into it, but I do want you to be somewhat exposed to it. All right. I do want those two values or those two formulas that you see right there. I want those written down in your code book because those are the two that you really need to have and really need to know. There's one more formula that we'll get to here in just a second that's also important, and that has to do with the resistors in parallel. You guys don't write this one down, but you guys may have seen the formula that's called the inverse proportionate resistor, inverse proportionate calculation for a resistor in parallel. And it is kind of complicated and not very easy, I think. You guys like fractions when you were in high school? Elementary? I know, right? So if I have 1 over R1 plus 1 over R2 plus 1 over R3, or however many resistors I have. So if I have resistors in parallel, I can't just add them up. It's weird. I have a 5 ohm, a 10 ohm, and a 15 ohm resistor in parallel, and if I add them up, it gets less than the smallest individual resistor value. So if I have a 10 and a 15 added together, it's going to be like 3.5. How do I add stuff that gets smaller? Right? Doesn't even really make sense. So when you're looking at resistors in parallel, I think that the way to kind of bear that in mind to make more sense is it's more like a pressure tank, right? If I have a series circuit where I've got one gigantic water tower with one pipe where all the water come through, that's a series circuit, and the diameter of that pipe, the length of it, and all the resistance that it has to go through, every bit of that pressure has to go through that one pathway. Make sense? So in the parallel circuit, it's more like basically a bucket where I put a bunch of holes in it, because what happens is the more pathways there is for that pressure to go out, the less the overall pressure is combined. Does that make sense? And so that's what's happening here with resistors in parallel. If I have a 5 ohm, a 6 ohm, 10 ohm, and a 15 ohm, I'm looking at the sum of all three of those being less than that smallest individual resistor. And it's usually somewhere about half or a little bit more than half. So 2.5 to 3 is probably what I would guess that would be. Now to calculate that, I would put these into this formula here, and I'd have to do 5 into 1 and 10 into 1 and 15 into 1, and it's kind of a mess. You got to convert those into decimals and add the decimals together, and then divide it into 1 again, right? So I would really prefer you to just forget about that one. There's another one that works with 2 resistors. This is a much more simple math. Basically, if I have just 2 resistors in parallel, this formula will be a lot easier to use with those 2. And furthermore, I can use it with more than 2 by pairing them together one at a time, or a set at a time. In other words, if I have 3 resistors here, what I can do is do the formula of these 2 here, right? Isn't that? And get one value for those 2 together, and then do that one more time in the same formula using the value that was combined here and then the other one together. Okay, so for example, RT equals R1 times R2. So in this case, we'll call this R1, R2, and we'll call this something else. So I've got, I love it. That is and then 5 plus 10 on the bottom. So I'm looking at 50 divided by 15, right? 50 divided by 15 is 3.33 ohms, right? So these two combined give me 3.33. Call 33 ohms, sort of put amps there on, okay? Makes sense? I'm looking at that 5, I'm looking at that 3, that number needs to be less than the 5, so I feel like that's probably a pretty good number, right? Now that I've done that, I can erase these two and go, okay, the combined value of R1 and R2 is 3.33 ohms, and now R2 then would be 15 ohms. I can just do the math. Make sense? That way I'm using a simpler formula. I don't have to worry about that inverse proportion crap, or excuse me, the inverse formula up there with the 1 on top of it. So I can just go back here and do, instead of 5 and 10, I'm doing 3.33 and 15. Make sense? And the best part about it is you can only have one formula to remember instead of 2. But you're going to need that one anyway, so now just use it instead of the other one exclusively. So 3.33 times 15 divided by, what is that, 18.33? 2.72 ohms total, and that's kind of what we thought it would be, 2.73 ohms total RT then being parallel. So the 5, the 15, and the 10, 5, the 10, and the 15 combined give me a value of 2.73, which is right at a little bit more than half, right? Which is kind of what I thought it would be. Okay. If you don't have that formula written down, it's in your book on page 27. Page 27 has a bunch of little formulas that I feel like are ones that are really critical for you to have handy. So sometime before you go take your test, everything's on page 27. What did I say? 27. Everything that's on page 27 should make its way into your back of the code book somewhere, because those are formulas that have to do with Ohm's law, voltage drop, and some other things that are kind of written at the bottom. So as you have time to get those to fit in, those are the ones that I would consider. That R1, R2 is at the very top of the page there, just so you know that's kind of where. Okay. Page 27. Get those all written in the back of your book. The notes at the bottom of page 2 as well. Yep. I'll talk about that in just a second. But you see the waves of R1 up there. This table that you're looking at that's colorful, that is a voltage drop table where the V is a fixed value. So where you're trying to fix your voltage drop at a maximum of 3%, a maximum of 5%, so what have you. Those are the values that we calculate out based off the common voltages that are out there. Okay? I feel pretty good about that. I feel pretty good about that.
What page were you saying as the,
27.
no, in the code book that has the space to write all this in?
Just one more time.
Oh, look at that. Thank you, sir.
Yes, sir. All right. All right, so is this, I'm going to assume that's parallel, I'm guessing. Well, let's work it out. I'll do it as a single phase calculation first, and then we'll go back to it with 3 phase.
I believe it was the second answer, maybe?
Answer C?
Yeah. And then it was like a full, I think it was 2.
480, was it a 40 to 40?
60, 40, 60, 50 to 40 ohms.
The 480 is a 3-phase voltage, so.
Yeah, it could be a single phase though.
I believe it was 2.
I've had some 40 volt single phase lighting. Yeah, I'm serious.
Alright.
How did I get the 480?
I
Is it
suppose if
stinger?
they aren't saying it's 3-phase, we're just gonna treat it.
No, I think it is 3 phase. I agree with you. What I said was going to do it as a single phase and a 3 phase, because it is different. I mean, different way of doing it. But no, I'm sure it's a 3 phase calculation. How did you get 480? Is that a stinger? Is it a delta? It has to be a delta.
We don't use it? We use 600.
Can you, 600, yeah.
So we use 600, 347.
Yeah, you're right.
Down here it's 480, 277.
It's a single leg off of a lighting. We're going to discharge metal discharge lights that were.
So I do
multi-tap.
discharge,
Yeah.
multi-tap, and if you were only using one leg, you must have used the neutral.
Yeah.
So that would run it down to 277.
No, it was, well, the lead was marked 480 and there was a 277 lead as well, so.
Oh, yes.
Anyway, that was just.
It's been sold, how long have we been using LEDs, because it seems like.
All right,
Now that I can't remember the last time I touched the ballast on a high intensity discharge light.
I've got resistors here, right, which means one thing and one thing only, and that is I'm gonna start with VAR, because that's really the only formula that I can deal with. And I'm sorry, the resistors are amps. Yeah, the resistors are right. All right, so I've got VAR basically is what I'm looking at, and they're asking me for the amps total, or just,
Maybe different amperage for each amperage.
what's the average of a
40 volt
circuit?
We're
I think it's combined, is what it looks like, branch circuit, we've got two amps there.
He's on the top question. I think
Very tough question, yeah.
Question number one.
Yeah. All right, so if I do, let's just do it parallel, right? We're looking at 40 volt and 60, 50, 40 ohms, and we're looking for amps, right? So if I were to look at the amps right here where this exists and it was parallel, 40 volt being the circuit voltage, then I would be in parallel, 480 volt would be my top value. My resistor value would be 60 ohms. I'd take 60 divided by 480 would give me the amperage for that resistor. I'm cautioning you that it is a three-phase probably, so it's really gonna be 830.4 divided by 60, right? But let's just do it as single phase first, just kinda don't break anybody's mind, so that's 8 amps. And then that's gonna be 480 divided by 50. What's it come out to be? 9.6, all right, and then the 40. Volts divided by 40 ohms. What'd you say?
Well,
Even. All right, and then parallel amps add up, so I'm looking at 12 plus 9.6 plus 8, that gives me 29.6 amps. Total amp capacity of the calculation, 6. Right, 29.6 amps. 18. In series, it has to be a parallel circuit. In series, it'll all be the same value, right? If we did it as a three-phase calculation, then you're looking at 830.4, because that 40 volt would have been 480 times 1.73. So 830.4 for each one of those three divided by those values would have given you.
You could also just multiply your answer by 1.73, you get the same thing.
You could, you're absolutely right, you sure could. Is it 830.4 or
830.
it's not, it's gonna be 277 because the 1.73 divided in each one of those, 'cause it's not gonna be, I can't use 830.4. That's not right, it's gotta be 277 volt, because each one of these would be an individual leg in a three-phase service, right? Or circuit. So it'd be 277 volt really, divided by 60. Otherwise, I'm gonna get too many amps. I'm gonna get an increase in value in amp capacity for a three-phase, which would not be the right way to do it. So 277 volt divided by 60, 277 divided by 50. Excuse me.
So would you be assuming that on the test? You know what I'm saying? If they didn't specify 277 volts, they're telling you 480 volts, and you're saying
So,
like,
what's
okay,
happening?
you're saying
No, what's
277
happening? I'm not
volts.
assuming anything. What I'm doing is I'm dividing the 1.73 at the branch to get 277 for each one of the individual calculations, right?
1.7.
I could probably,
You said you could add-
I could probably add those resistors in parallel together and get a total RT and then do it at the branch at 480 times 1.73 divided by whatever that total sum of resistance value, and it would be the same answer. Bless you. But my point is that when I have a three-phase system, my amp capacity gets to be less, not more. So if I were to do 480 times 1.73 here divided by 60, that's gonna give me a bigger capacity for each one of those values. So my total capacity would go up, not down, which is the wrong direction, right? So it's gotta be 277 divided by 60, which would be 4.61. I'm just gonna write this down. I don't really, wish I knew a little bit more what that question was, but he said at least it's 2, and it's not even, yeah. I'm glad we looked at this before letting you loose with it. 50, 5.54. That doesn't, I don't see them doing this either, so I think what we did earlier was probably a little bit better, because I don't see them using such odd values like this. So I'm pretty confident then that's gonna be a single phase calculation, just because of the way that this math is coming out, but, 277 divided by 40. 6.925. Unless I add these together and they end up being a whole number, that's 16 amps. 4.6 plus 5.4 plus 1707, or somewhere in that area.
So, okay, so to do it another way is to just use 480
Mhm.
and then take your final answer and divide it by 1.73 and end up with 17.1.
Yeah, same.
So you can do if you do your root of 3 at the end, you're doing less math.
Okay, makes sense.
Right, do you guys understand what the root of 3 is for?
What, no, what was it?
The root of 3 is anytime you have 3-phase power, you
Okay.
need to
Multiply.
multiply or divide your answer by the root of 3.
What is, how'd you get the number though, the root of 3? So how'd you get that 1.7?
1.73 is
Is
the
it
root of 3.
trigonometry function?
Oh, okay.
It never
Square root of
changes.
3 equals 1.7.
Okay, cool. Got it.
But if you take 480 volt and divide it by 1.73, what do you get on your calculator?
277.
So I mean, that's
That
basically
works out the
what's
same.
happening. If we're dividing it, we're taking it into single phase
It's a little
277.
faster, huh?
Well, the thing is whichever way you do it, always do it the same way.
Yeah, right.
I was taught to always do the square
Be
root at
consistent.
the end, so that's what I do. And it's less math. So what you're saying?
For me, I'm comfortable,
How do you say it?
I'm comfortable converting things to amps because I'm
Yeah.
used to
How you
that,
do
but
it?
I don't need- honestly, though, I don't want to get too lost in the weeds with this because I don't really know exactly what the question's asking, but I guarantee you, just looking at the way this is coming out, I guarantee you that they're doing this as a single phase. I mean, it's just too messy otherwise. There's a lot more math here and a lot more calculus.
I would think that for a question like that, they would say if it was 3-phase or single phase.
Absolutely, yeah.
That's just too juicy of a.
Well, it'd be two totally different answers, both of them correct, depending on which one it is.
Yeah, that was just too juicy to let them.
All right.
Yeah.
All right, that's all I want to talk about with Ohm's law. Voltage drop, I don't see much voltage drop on the test, so I'm gonna skip it.
Yeah, there's not really that much,
We're
man.
not doing voltage drop?
There's barely any.
On page 31, I want you to take a good look at my can lights.
Do you have where to find the stuff to do that?
Yes. There's a whole section right below. Y'all like my can lights? Look on page 31.
What the heck?
Maxwell House can lights. Yeah, exactly. That is a can light. I don't care what you want to call a can light, that's a can light.
Rated for what location?
Yeah, that's right. Just using the caulk. All right. This page is a must-read page, right? This is just a list of things that I feel like are so important that I want you to make sure that you read it all the way through. So if in doubt, read the whole article if you have to, right? But what I've got listed there specifically, just to make it to call out to you, is I've got 250.20. So in other words, rather than having to read the whole article 250, I've got specific sections broken out for you there. So I want you to spend some time going through those and make sure you read those thoroughly, underline them, use that index in the back to kind of cross-reference stuff again here.
Yeah, I know that there was quite a bit of the separately derived systems and supply jumpers and all that jazz on the test.
So when you're talking to me about that, what you're telling me is that 250.102C1 is what they were the parallel runs of conductors and
Yeah,
things of
stuff like
nature?
that.
All right, similar derived systems, they're all over the code book, so they're in chapter 7, they're in chapter 2, they're all over math, but, all right, and did I mention to you guys the homework assignment and the articles in the back, right? I told you about this in the back, right? You all know that that's also part of it. So you got your
Cheat
monthly
sheet.
stuff on 31, you got your tables that I mentioned to you that are specifically back in page 20 or something that I want you to go through. So that's kind of your homework setup as you get ready for your exam, okay? Now, I need to go back real quick, and we need to just do one quick, no, I don't wanna do that, you guys don't remember that, we're gonna move on. All right, check our wire and patch, we're good with that. The next thing we need to talk about is service calculations, specifically, ranges, dryers, and some other sections. So in my code book, or textbook on page 51, and then we're gonna do more up to that. If you think about the code book and kind of what its roots are, from the perspective of it was written by insurance agencies based on the damage they had to pay out, right? And the idea was minimizing that cost layout that they had to pay for people perishing in fires, things of that nature. And so it makes sense then that in a residential application where people are asleep and they die because of a fire that's caused by electrical installations that are shoddy, that's a pretty high payout, right? So you will see a lot of residential driven codes in the code book, a lot more than you do specifically in commercial, specifically because that's where the money's at, right? When it comes to fault or damages, right? Human life being a incalculable value versus some commercial building where there was nobody in it that burned down the ground, and it's just a monetary loss, but it's not incalculable like you lose a family, right? So that's kind of sobering. I mean, you get that Ramos, but sad over, but basically that's what this code book is written about. And so if you look at 220, you'll notice that when we're talking about load calculations, there's a lot of calculations in 220 that are residential and not so many for commercial. Right? And you, I mean, as a commercial electrician, I always wondered, why is it that we don't have more commercial load calculations in the book? Well, in a commercial building, if it's there, you count it. I mean, there really isn't a lot of derating factors in a commercial building because you have loads that are sometimes constant and sometimes they're all on at the same time, right? So I don't really get that diversity of some stuff not being on at the same time like you do in residential dwelling. So the one thing I wanted to talk about real quick though is branch circuits versus feeders. And that's really the big thing that people get confused with when we're talking about load calculations, right? There's a lot of tables in the book that have those factors that we talked about yesterday. Like if you look on page 95, there's a table up here for lighting load demand factors, and they've got percentages there. If you look at the one on the bottom of the page, 220.47, that's for receptacle demand loads. You've got the dryers that we talked about briefly earlier. We've got the range table. I mean, all these tables have all these demand factors in it. The one thing to remember is that as a branch circuit, right? When I'm calculating a branch circuit, I'm looking at all the values on that branch circuit and I'm adding them together and I'm sizing the breaker based off that number. There is no derating happening on that branch circuit calculation. Let me say that again. On a branch circuit calculation, I can't take the risk that everything might be on at the same time. I can't take the risk of ignoring that. So when I'm sizing a branch circuit, there is no derating that's going to happen, okay? Don't derate a branch circuit. In other words, a connected load and a demand load for a branch circuit are probably going to be the same number. The only time it'd be different is if it continues due to load values, right? We're going to increase it instead of decreasing it. But branch circuits don't get derated. For the love of God, if you're in this code book and you're trying to take a demand factor and reduce a number, and the question is asking for a branch circuit, I'm going to pop up behind your head and slap you in the back of the head. It's like a magic things are going to happen, right? It's really one thing you got to be very careful of. Branch circuits don't get derated, and I can't say it enough. Now that you know that, okay, the Article 220 is laid out in a real peculiar manner, and it took me a while to figure all this out. But if you look at the part numbers, right? In this case, the part numbers are really critical to understand what's happening here. If you look on page 92 and 93, or somewhere in that vicinity, the beginning of Article 220, where it has the actual grade heading there in 220. What page are you on?
93.
Page 93, and mine's on page 92, so it's really pretty close, right? Part 1 starts at the very top where it says general. And I like the little graphic that they have right below that, which shows you kind of how the parts tie together. I'm going to skip that just for now, but it's a nice little picture, and we'll come back to it in a minute. But if you look on the next page, on the next column where it says part 2 says what? Let me tell you something about these part numbers. They disappear into the page and you never even see them, right? They're not set to the left, they're set above the section and your eye never catches them, but they're probably one of the most important flags or tags that you need to be paying attention to So in my suggestion, I would go through your code book, especially in certain articles, 230 being one of them, or 220 being one of them, and I would highlight those part numbers with a different color highlighter when I put on my text so that it makes them stand out a little better, right? Part 2 says branch circuit calculations, does it not? And if you go a little bit further down, the next page, you'll see part 3. What does part 3 say?
Feeder and service.
Feeder and service.
Bam, now that's the thing I'm getting at, feeder and service calculation. So as a branch circuit, I said earlier, it's really true, on a branch circuit, what is it that never happens?
Don't do
It only rates 100% of that value. That connected load and the demand load are probably the same value, right? I don't have a diversity happening here because the risk is too great that they might come on. But on a feeder, well, once I start putting a bunch of 20 amp breakers in the panel, then I don't have to worry about them all being on at the same time. And that's why I don't have an 840 amp breaker in the top of that 42 space panel. It's that 20 amp branch circuits, right? Because I take that diversity factor and I'm basically taking a chance that all of that stuff's not gonna be on at the same time, right? So that's gonna be where the derating happens. If I'm derating something, it better be a feeder calculation, it better not be a branch circuit
So
calculation.
if anything falls under branch circuit loads.
Leave it alone, don't try to take any
Well,
table
there's a
bags.
section.
Yeah, if you notice that part 3 where it says feeder calculation, that happens, in my case on page 94, that happens before any of the tables that have derating factors on them. In other words, every table that has derating factors on it is part of part 3, which is a feeder calculation, not a branch circuit calculation. Now, do you know that? The distinction when they tell you or ask you to calculate a branch circuit is vastly different than if they ask you to calculate the same thing, but as a feeder calculation, right? I'm gonna use the same beginning calculations that are in part 2 for both feeders and branch circuits. The difference though is I've got one extra step when it comes to feeders where I don't have that step with branch circuits, okay? All right, all that being said, I think that kind of gives you a good idea of the way to look at this. And that's really important. Part 2, part 3, and remember these tables you see back here only apply to feeder calculations, not to branch circuits. So they could ask me, well, let's talk about, the multi-outlet assemblies. Where are those? 220.14 used to be H. Yeah, on bottom page 93 under H1 and 2. Real quickly, I'm not going to get too deep into it, but multi-outlet assemblies are plug mold strips. They come pre-manufactured with a receptacle outlet about every 12 inches spaced out on the strip, right? All right, so really, multi-outlet assemblies, M-O-A, given the fact that they're in a length of wire, or length of metal there, with one receptacle about every 12 inches, well, guess what? These are general purpose type setups because I don't really know what you're going to plug in. So I'm not worried about continuous duty in these types of calculations. But what I am worried about is the whether or not the things that are plugged into it would be on at the same time or not, right? And so simultaneous use is the way they approach it, right? If I've got 5 things plugged into this 5-foot strip, and these 5 things are interlocked from each other as a process, we're not like in a lab or something where I got to do step 1 before I do step 2, step 3, so on and so forth, where I know that linear process won't let them be on at the same time, then that's a non-simultaneous use plug mold strip, right? And that's what H1 is talking about. Where they're unlikely to be simultaneous, then every 5-foot section is going to be watered down into a single count that equals 108 volt amps. Okay? Now, if you ask me, the nature of what a plug mold is that you can't guarantee that stuff wouldn't be on at the same time. I mean, that's kind of the whole point of something like that is so you can plug a bunch of stuff in there and hopefully it'll be on. Some parts will be off, other parts will be on, but if there are 2 of them that are on at the same time, that's simultaneous use, right? So if it's simultaneous use where more than one of these things could be on at the same time, then every foot counts as 180 VA. So that's the difference. H1, I'm watering this 5-foot section down into 1 count, but when it's simultaneous use, then every single foot counts. So if there's 5 feet, it's 5 times 1 count, which is 5 times 180 VA. So it's significantly more calculation-wise than what the non-simultaneous use would be, okay? Non-simultaneous have to be done by each section because if you're not careful, what would happen is that these were multiple links of separate plug holes, right? So I've got another one that's 4 feet, and I've got another one that's 6 feet, right? So I've got a 6 foot section, a 5 foot section, a 4 foot section. I have 3 separate pieces. If I add all those together first and divide them by 5, I'm gonna get less than if I do them individually. Because the way this is that it's every 5 feet or fraction thereof. It's not major, it's fraction. So in other words, I go one section that's 6 feet would actually count as 2 counts, because I'm gonna get one count for the first 5 foot, and then the extra piece that's left over, whatever it is, would also count as another count. So I'd end up with 2 counts for that one count for that one count for that one, total of 4 counts. But if I were to add these together, I get 15. If I divide that by 5, I only get 3 counts, right? So as a non-simultaneous application, H1, I cannot add them together first. I have to do each section individually, and I'm gonna round up anything that doesn't equal exactly 5. Or if it's less than 5, it also counts, right? So a 3 foot or a 4 foot would also count the same as a single 5 foot section, okay? So it's any fraction for a 5 foot section, it counts as a single count. All right, so non-simultaneous, really, we're watering them down, so we're getting a lot smaller number than we would if they were simultaneous in use. So it takes a lot of these to really get there. But as a branch circuit, that's all there is that is talked about here, is a calculation for a feeder. If you look at the table on page 95, that's 220.47. So it says demand loads for non-dwelling receptacle loads, right? Everybody see that really tiny table? It's got 2 rows on it. It's really kind of a small table, but it's a table nonetheless. 220.47, demand factor for non-dwelling receptacle loads. Now, is this a non-dwelling receptacle load? Yeah, maybe, probably, most likely, but not always guaranteed. It could be residential. So I probably wouldn't calculate it the same way. But at any rate, I would still use this table though for this application. If you look at the article, it is the same under 220.47 or above. It says other dwelling. It says receptacles calculated in accordance with 220.14H are allowed to be derated by this table. So what's happening then is I know, because of the way that worded, that I have permission to use the derated table for these calculated values under 220.14H if I'm doing a feeder calculation. Okay. All right. The way this table works is the first 10,000 kVA I can't touch. So if I do a load calculation, let's just say I had 23,000 total VA of load. Susan? Sorry. If I did a load calculation on a bunch of multi-outlet assemblies and I had this total calculated value of 23,000 VA, and I'm doing a feeder calculation, then I'm looking at this table going, okay, as a feeder, the first 10,000 of that number I can't derate at all, right? So I'm gonna take 10,000 and just put it over to the side. I'm not gonna subtract it, because I don't want you to think we're getting rid of it. We're just gonna move it out of the way. And the balance of the 13,000 that's left over, I'm taking a 50% derating factor, because that's what that second row is. So the first 10,000 I can't touch, so I'm gonna put 10,000 over here in the bank and just kind of hold on to it. And that leaves me with 13,000, right? So the amount that's above 10,000 is what that 50% would be applied to. So I take 50% of that 13,000 would be what?
6,500.
7,500. 7,500. So times 5.
6,500.
65.
6,500.
6,500.
16,500, yeah. Total, sir.
And then add that to the 10,000, so 16.5 kVA as a final demand load, right, for your feeder calculation. As a branch circuit, what were my answers for the branch circuit calculation? Same question, same 23,000 total VA broken out. As a maximum demand on the branch circuit, what would the number be? 23,000, right? Because don't derate a branch circuit for for this table wouldn't apply, right? That's what I'm getting at. So as a branch circuit, I have to calculate 100% of this load. I'd have the number of circuits, whatever number of circuits I would have to have to distribute it, but I wouldn't be able to derate this number. I'd have to keep all of it, right? So branch circuits, 23,000 VA would be my answer. Feeder calculations, it would be 16.5 based off the application of the table, given that we're hoping for the diversity of things to kind of work out, okay? I'm going kind of fast, right? I get that, but just a lot to kind of cover. So if you have any questions, don't hesitate to speak up. Receptacles, under 220 dot, well, this is kind of confusing because they can move this around. But receptacle outlets, if you look on page 94 in my book, it is 220.14I So it's on the left-hand column at the top of page 94, where it says receptacle outlets. It says I in receptacle outlets. Yours will be somewhere in that same vicinity. To the left of that, I want you to write the word commercial and make it big so you see it. What I'm trying to say is that section J below that deals with other receptacles that are non-commercial. Section J specifically has to do with office buildings, which we'll talk about in a minute. But receptacles that are in a residential dwelling are in 220.41 at the bottom. So what's left over then for receptacle outlets under I is basically anything in a commercial building, right? It's not an office or bank. All right, it's real simple. If I have, go ahead.
So they don't consider an office or bank commercial building?
Well, they do, but they consider them special because of the number, just the use of those two occupancy types is heavier.
All right.
Like in a grocery store or something, your general purpose receptacles are really only used for cleanup time and stuff like that, but in a bank, they've got all kinds of things to plug in, so it's just a heavier demand on the current circuits there for general purpose receptacle calculations. All right, so under section I, it's basically, all right, let's talk about a yolk. Anybody know what a yolk is?
Yes.
It's the yellow thing inside an egg, right? Well, that's what it is. Huh? What is a yolk? I don't know, they don't define it.
It's the straps that the receptacle's built on, or like.
If I have two oxen, and I want to put them together, I have to use a yoke, right? That way I harness both of them together. Same thing applies when I'm talking about a receptacle and a receptacle. If I want to harness them together on the same device, I put them on a yoke, right? So I'm yoking those two receptacles together to give a single device. So the yoke is a single gang, is really what we're talking about, right? The strap that holds the device into the box that takes up a single gang. Every one of those yokes, or in my case, I look at it as a gang, is an equal value of 180 VA regardless of the number of receptacles on that yoke. When I say that, a duplex receptacle's got two receptacles specifically on that single yoke, right? The single gang, that would equal 180 VA, right?
No.
A simplex with one receptacle in a single gang would also count as 180 VA because it's the strap or the yoke that counts, not the number of receptacles. So that's also 180 VA. A quad, which is two gangs, each one of them having receptacles on both sides, would be 360 VA because it'd be 180 VA for each one of the two gangs, right? All right. It doesn't count the actual receptacles except or unless the last part of that section there talks about if you've got a single piece of unit equipment where it's built into the equipment itself. If you have 4 or more receptacles, then instead of doing it by the gang, we do it by the receptacle. But it's a very special application, and so I haven't seen a question about it in such a long time. I don't really want to tell you about it, so we'll just leave it at the gang being at 180 VA. The way they word these things, they'll say, okay, well, given a residential, commercial building, and you had X number of receptacle outlets for general purpose receptacles, or outlets for receptacles. When they're talking about the outlet, they're talking about that box that we're going to put that device in, right? They're not really talking, when they say there's 60 outlets for receptacles, they're not saying there's 60 receptacles, they're saying that there's 60 gangs of outlets, whether that be duplex or simplex, they run that. Make sense? All right. I don't care if it's 15 amp, I don't care if it's 20 amp, I don't care if it's GFCI, I don't care if it's non-GFCI, I don't care if it's USB. If it fills a gang and it's a device and it's receptacles, it's 100 MVA, right? So it's really not, it doesn't really matter to me what the ampacity of the device is. It's just the gang that it fills, the fact that it's a device or a receptacle, okay? All right, that's all listed under section I there. So let's say that we had a restaurant where we had a bunch of receptacles listed out there, but I'll just give you a total of 165 outlets for receptacles, and we're in a restaurant. I don't know how to spell restaurant. There you go. Don't know that. I don't know how to spell it, do you? I said it, you guys.
Where's that restaurant?
That is a good restaurant.
There.
Anyway, lectures of the world's worst spellers, and you guys know exactly what I'm talking about. All right. So each one of those outlets for receptacles is going to be applied under 220.14i at 180 VA for each one of those. So I'm going to take 165 times 180 VA. What's it?
29,700.
29,700?
Feel free to double check.
I don't know if you guys can see that.
27.9?
I'm gonna go with it. I'm happy with it.
29.7.
29,700.
There you go. Your list next year. got it.
There we go. Yeah, it did. 29,708, right? Agree with that? All right, what do we do next? Well, it depends on if I'm doing a branch circuit calculation or a feeder, right? If I don't tell you it's a feeder, well, I'm going to say one way or the other. I mean, on the test question, I'll ask you one or the other. But if in my case, did I say one or the other? I didn't really say it, did I? All right, so as a branch circuit calculation, that 29,708 is my answer. That's the demand on the branch circuit. Don't get ready, right? As a feeder calculation, I take the first 10,000 that away. 19,700 left over will be divided by half, or times 0.5, and then add.
9,850.
Is what 9,850 is a half of that?
Yeah.
Plus
So
10, 19.
19,850.
19,850, or in the case of the branch circuit, 29.7 kVA. Okay? Don't derate branch circuits. Okay? All right. Now, in banks or office buildings, now we stopped calling them banks because it says under section J right below that receptacle outlets in office buildings, but if you look at the table that's over here, 220.42A down at the bottom, they have a note number 4 that says banks or office type occupancies, right? So really, it is still banks or office buildings, and so I want you to write that next to that office buildings. You put or banks. That way you remember that that applies to both banks as well. I'm talking about 220.J, which is right below the section I was at. Yep, and the reference that I gave you, it just says office buildings there, right? But if you look at the table that's on 220.42A, the lighting table, I don't know which way, yeah, right there. The note 4 down there at the bottom says that banks are office type occupancies, right? So basically, it is banks and office buildings still, even though they kind of changed it. I like this because now they've broken it out into branch circuits under this section we're talking about here, and they have feeder calculations separately. If you look at 220. Where is it?
43?
43 is it?
Yeah, options.
Yeah, I'll put it right there. So the difference here is that the branch circuit is the 220.14J. The feeder calculation is 220.43. They look very similar to each other, but because of the application of the derating factors being kind of confusing, they've spelled them out into 2 different sections now, but it's the same math, right? What's happening here? What's happening here is that, like for example, in my office, in my residential house, right? I've got 4 receptacles in that entire room. There's one on each wall. It's kind of a small room. So I've got in my office 4 monitors, 2 computers, a laptop, an iPad, 2 cell phones, 2 headphones. I mean, I've just got a bunch of. I literally have. You know, you get those 9-packs that go onto the duplex, right?
Oh,
You seen
yeah.
those before?
Yeah.
And I got another 6-pack on the bottom of that. So and then I've got all kinds of plug-in strips because I know what I'm doing, right?
Hey, it's kinda like a mobile mechanic.
Non-simultaneous use, right? Anyway, the point is that they saw me coming a long time ago. They know that in an office environment, I'm gonna overuse those general purpose receptacles way more than where you would in another type of occupancy that has less use of it. So because of that, I've got this minimum calculation that I have to do, which is effectively what number 2 is. So J2 says, look, no matter what, I can't have a value attributed in a calculation that's less than 1 VA per square foot to be added in for receptacles, regardless of the number of receptacles that I have. Now, I could be looking at a set of plans for this restaurant, and I could see this 165 receptacles spelled out. I could count them all out, right? But the square footage of this restaurant could be 28,000 square feet. That's a hell of a restaurant, isn't it? 28,000 square feet. That's a nice. Was that a Hollywood? One of those Hollywood? What's the Hard Rock Cafe? Yeah. Didn't those collapse not too long ago in Miami or something? Anyway, 165 receptacle outlets. My load calculation for the branch circuit was 29,708, right? So if you look at the section dot 14, J, the very first, number there says calculated load from 220.14i, so effectively they're telling you to do that same math that we did a minute ago, where we take the 180 VA for each receptacle outlet, and then that number, that 29,700 VA is the resulting value for the branch circuit, and then that's basically what number one does. And then as a separate calculation, I look at the square footage and multiply times 1 VA per square foot, so in this case, the 28,000 square feet times 1 VA would be 28,000 VA, right? No, I just look at these two separately, right? And whichever's the bigger number would be the load calculation for receptacle that I got. Okay? I'm not derating anything here, because I don't derate branch circuits, do I? Okay.
No.
Now, as a service calculation in the other section, which is the 220.43, there it does tell me that I will take the demand factors when I'm doing the 220.14i. So this math right here, where I'm doing this 29,700, under the feeder calculation in that second section there, it tells me to take the derating factors like I would as a service calculation, right? So I'm gonna end up taking the first 10,000, divide, and then 50% of the rest of it, and that's what this number was right here, right? The 1980, right? That's what this was. Okay. So then that becomes my load value for number one, or K1. It's not K1 anymore, it's dot 43.1. Make sense? But then I still have to look at the square footage times 1 VA, because that's still the same calculation there. So then I have this number here and 28,000 VA, which is what the square footage times 1 VA in this case. Then the larger value is going to be that number 2. So I end up, yeah, come in here. Yeah, please. Yes, thank God. No, it's in here. Hey.
Hey, my friend.
Who ordered pizza? That's nice, you guys.
You know, figured out my.
Anyway, so what I'm getting at is the branch circuit, this would be the larger number, right? The sum for a branch circuit under that first section, the dot 14J, I'm looking at 29.7. Under the second section, this becomes a bigger number because I derate the first one, but I don't derate the second one, right? So no matter what, don't derate the square footage on either way. I mean, the square footage is the minimum threshold amount that I have to calculate. In that case, a 28 kVA or 28,000 VA would be the answer for the feeder calculation. Okay? Can't make this shit up. It's really cool.
He got real happy when the food came.
Yeah, I'm telling you. Do you have a second copy of this? You can take a picture of that and then text it to me.
Yeah.
Appreciate it. And then give that to the young man back there. I say young man, because this young man, I'm 50, I don't want to say how old I am, 54.
Oh, you're young.
I just had a baby.
Oh, man.
Hell.
I'm trying to be like.
No, I used to think I was smart. Hey, I'm not. Do the math on that one, huh? Ooh. All right. Let's take a break and eat that pizza before it gets cold, and when we come back, we'll pick back up. About 15 minutes. Go get yourself a drink, a beer or something.
Don't tell me that.
Yeah, so she'll email you a link, it's a private link. I don't.
My wife just remembered me, if she tells me we're having a baby, we're going into a rich fella.
We'll take it to YouTube, but it will be a non-public visible video, basically, that's why you have to. Yeah, if you haven't got that by Wednesday or Thursday, text me, make sure you get it. It's up to me to get it off my phone and upload it, so it's just however long that takes me, usually Monday or Tuesday, but with that, solar eclipse, I may be kind of tied up Monday. I don't know. You think it's gonna?
Is this your number?
Well, maybe nobody.
This one, right? Is your cell phone?
Yes, sir. Yeah, they're 914.